Welcome. In this session, we'll explore the Lagrange function for a constrained optimization problem that comes from basic physics or mechanical engineering. And what we'll do here is we'll imagine that we have a system that has two ideal springs and one mass and an external forcing function. So what this will look like is we'll have one spring, and that spring will have a spring constant, which we'll refer to as K1, and the extension or compression of that spring is going to be our first variable W1. We'll have a second spring, which has a possibly different spring constant, and the displacement of that spring will be our variable W2. And we'll imagine that these are connected by a single solid mass. And if this was an ideal system, what does that mean? Well, for example, if these springs were somehow created out of superconductors and the whole thing was conducted in a perfect vacuum, this mass spring system would oscillate back and forth forever. But in reality, it'll settle down at some place. And if those spring constants were exactly equal, it would settle down where W1 and W2 are both zero, right? And if the spring constant, for example, for K2 is larger, then that means it'll be a stiffer spring, and so in its resting position, it'll push against K1, and the mass will end up being displaced slightly. Well, what we can do is, if we were to tip this sideways and imagine that mass is subject to gravity, what we could do is we could say, well, there's an external force that's being applied to it. So here are the variables and the constants, is that each spring will produce a force, and we'll refer to this force as C. The reason is that if we referred to it as F, we might get it confused with our objective, right? So we'll refer to that as C, so there will be C1 and C2, and each of these springs will have an internal potential energy, or a spring energy, that we'll refer to as Z sub I. And as I mentioned before, the stiffness coefficients we'll call K, and the displacements will be the variables of our problem. So what we'll have is that the force is linearly related to the displacement by the spring stiffness, and the spring energy is the standard potential energy term. Now, let's write down our objective. Let's refer to this as, so we'll write down our governing equations again, which is that force produced by or on spring I is the spring constant times the displacement. So W1 and W2 are our variables here, and the energy in that spring is 1/2 of the spring constant times the square of the displacement. And we can then gather these, and we can say that the objective function, and so we used F1 in the previous session, here we'll use F2 of a vector argument, will be the sum of the spring energies. That is, we're going to say that nature will put that mass spring system at rest where it's minimizing the sum of the energies, and you should work this out. You should work out this sum and figure out that this actually works. I'll write that as 1/2 of the argument vector times a symmetric positive definite matrix times the argument, and here we'll note that is where this matrix will be, it'll be K1 and K2 on the diagonal, and then the off diagonals will be 0. So what we have, so this would be the unconstrained problem, right? And so in the unconstrained problem, we would just try to find the minimum of these, which is what we would try to do, is we would try to find the W vector and its entries are the spring displacements that would cause this to be minimized. Now, we have an additional constraint, which is there's this external energy that's being applied to our system. So the constraint is that forces have to balance, and the reason is that from Newton's third law, F equals ma. If the force is non-zero, then the mass is accelerating, and so it's moving, and we want to consider where the mass is not moving. So our constraint is that when we take into account the signs of the different functions, we want the forces to be balanced, and so normally we would say that's zero, but in our case we might have some external force that's being applied, and we can express this using this equation that is equivalent to saying that this is, oh sorry, that's supposed to be a 1. So that would be equivalent to saying that minus K1 times W1 plus K2 times W2, and then minus that external force has to be 0. That is, this is called in physics or mechanics a force balance equation. And that is, for the system to be at rest, all the forces have to add up to 0. So what we would do is we will write our constraint, so let's call this our second property function of the vector argument, as being, we'll write that as a 1 form times the argument minus the external force. And now I can write the Lagrange equation. And that would be, so the Lagrange function would be function of vector argument and the Lagrange multiplier, and that is, now I take this to be 1/2 of W transpose K W, and then I add the Lagrange multiplier times the property, so that would be the 1 form m times the W vector minus the external force. And as before, what I do is I differentiate this. So the derivative of this with respect to W will be, so the derivative of that is 2 times 2 over 2, that cancels, times W transpose K, so that would be W transpose times K, plus, and that would be the derivative of mu times the external force is 0 with respect to W, so that would be plus the 1 form times mu, and then the derivative of the Lagrange function with respect to the Lagrange multiplier will be, that is 0, and that is just the property, which is m W minus CE. So that means that so now what we can do is the same as we did before, is that we'll write this down and we'll leave a bit of space, and when the transpose of the first equation is the 0, 1 form, when the transpose of the first equation is the 0 vector, that will be, let's just write a 0 vector there. And the transpose of a scalar is a scalar, so I can just use this directly, and that would be, I take the CE over to the other side, so that's CE. And then this will be, well, strictly, the transpose of W transpose K is K transpose W, right? But K is symmetric, so I can just write K down. So that will be K. And then when I go through this, when I transpose that, that will be the 1 form transpose times the scalar. And then this equation, I'll just have the one form, plus, and then mu is not appearing in that second equation, 0. And this is a linear equation. Now let's just check. This will be, this is going to be always a symmetric, positive, definite matrix. It has to be because the spring constants have to be non-zero. So it'll be symmetric, positive, definite. And then this is coming, so what is the one form m? Well, that's the spring constant. So that has to be non-zero. So that means that these entries are non-zero. This is non-zero. So this has to be a full rank problem. So that means it has to have a unique inverse. So that means that there can only be one solution. So that means I can put stars there and find the unique solution. So for example, with the first spring constant equal to 1, the second spring constant equal to 2, and the external force equal to 6, I encourage you to possibly type this into MATLAB and figure out this answer. What I get is that the optimal displacement of the springs is -2, 2, and the optimal Lagrange multiplier is -2.